seminar on high-entropy alloys. We are very glad to receive today to Dr. Mohammad Naeem, who is coming from the City University of Hong Kong. I will read the short bio of Dr. Naeem. Dr. Mohammad Naeem's background includes a bachelor's degree in metallurgical and materials engineering, a master's degree in materials engineering, and a PhD in materials physics. Sorry, before continue, I want to know if you can hear me very well at the back part. Okay, thank you. He has been a full-time teaching faculty of metallurgy and materials engineering related subjects in the Pakistan Institute of Engineering and Applied Sciences. He is currently a postdoctoral researcher at the Department of Physics of the City University of Hong Kong and a co-supervisor of 2 PhDs and 5 undergraduate students in Hong Kong and Mexico. The focus of his research is on the formation behavior of multi-component alloys under extreme thermal conditions. He employs neutron scattering for the in situ structural characterization. Dr. Naeem has been awarded the Young Research Fellowship by the Asia-Oceania Neutron Scattering Association, as well as the prestigious Marie Curie European Fellowship. He has been visiting various international large-scale neutron scattering facilities, including the support for designing and the execution of neutron diffraction experiments. He has also received the award of Best Paper on Materials from the Hong Kong Institution of Engineers in the 2020. His work has been published in well-reputed journals, including Science Advances, Acta Materialia, Scripta Materialia, Applied Physics Letters, among others. He will be the chair of the Gordon Research Seminar on Structural Nanomaterials in Switzerland in the 2024, to which all of you are cordially invited. So please help me to welcome Dr. Naeem to this talk. Thank you.
Hello everyone. Thank you, Dr. Liana, for the introduction. Can everyone hear me in the back? No? I don't know, this is often. Okay, I will try to speak a bit louder, maybe you'll be able to hear me. Okay, so today I will be talking about something which I've been working on for some years, but I will be giving kind of general introduction. So I may now not go into much details. I will just be kind of like, because it's a whole field, and I will try to cover like a bit introduction, and then I will try to introduce a bit of my work which I'm doing. Thank you. I think now no?
Is it better?
Is it better? No, it does not get better?
No.
How about now? Okay. Okay. Now? Okay, nice. Okay, so I will introduce a little bit about background for high entropy alloys. Some of you may have heard this name, but others may not have. But I think all of you might be familiar with alloys. So we'll start with that, and then we'll see what you can learn new. And then I will also, because I mainly work on mechanical behavior of high entropy alloys, and in particular at low temperature, cryogenic temperature, and with the neutron diffraction. If any of you have attended the previous, I was giving this class from 3 to 5. So if you are you are there, then you would know like what I'm talking about. Okay, so let's see what we can learn in this. Okay, so usually like mainly when we talk about alloys in metallurgy, they are mainly consist of one main element, and the best example is steel. So in steel, in steel we have iron as a base element, which can be as much as 90% and maybe up to as least as 70%. And then we can add some alloying elements like chromium, manganese, nickel, cobalt, and so on to improve its properties. Similarly, we have titanium alloys, aluminum alloys. So whenever you hear name, so they are like based on some element. Aluminum alloys, so mainly it's going to be aluminum, then some addition of other elements to optimize its properties. Similarly with titanium, for example, one of the most popular titanium alloy is titanium, 6 aluminum, 4 vanadium. So you have almost 90% titanium, 6% aluminum, and 4% vanadium. So that's how metallurgy has been for last how many centuries, like since industrial age, since industrial revolution. So, but in like we really focus on like pure things, in like the rest of the world, like okay, pure like pure passion. So there was this article in 2003 in Current Science, and its title was Alloyed Players, Multimetallic Cocktails. And I will read a couple of sentences from this article, and you can also read that in English language, or like in any way, like we always like focus on pure things, so that will be more precious. When it's impure, then it can be like less. So you can read that English language insists on unalloyed players, thereby implying that the sensation of pleasure must be pure and not admixed with other emotions, right? But what we do in metallurgy, we do exactly the opposite in metallurgy, right? Because in metallurgy, pure metals have very few uses. They cannot be that strong. If you use like I think everyone here is from metallurgy. Like we want to make metals or alloys stronger and ductile. So pure metals have very few uses, and we can always improve their properties when we alloy them with. So when we like make them impure, they will become more useful. Okay, so this is where we start. And if we look at materials, how the materials have their importance since civilization started. So it actually did start with pure metals. You can see that gold was the most important. I mean, you can see these are different kind of materials, but for us, metals and alloys are the most important. So we are going to ignore all of this. We don't care about them, at least in this seminar. So you can see, like in the beginning, it was gold, copper, pure metals, because humans thought there are a number of reasons, because they were readily like made in pure form, because they were kind of not that reactive, so they could be separated from rest of the minerals. Then we entered into Bronze Age, and it was already an alloy, right? But then really from here, like 1500s onward, there was always alloy of something. So cast iron, is alloy of carbon and plus few other things, but mainly carbon. Then really things took off, then we call industrialization, industrial revolution. That was when steel was introduced in, say, 1800s, mid-19th century. And from there, steel have been really one of the most important alloy. Even today, like when composites and the polymers and the other kind of materials, still steel is one of the most important structural material. Its importance have not decreased for at least last 2 centuries or so. And then you see, like there was, of course, alloy steels when like people added more alloying elements to make it stronger. That was the main objective. And but then it was heavy. So when vehicles or automobiles came into use, then we have to have fuel optimization. So then you should use lighter elements so that it can have less fuel consumption. Okay, sorry, am I speaking too fast? Yes? No? Okay, a little bit. Okay, I will try to slow down a bit. Okay. Okay. Okay, then we had other kind of alloys, right? As I mentioned, like they were basically, in all cases, without any exception, there were one main element, whether it was iron in this case, either it was aluminum, titanium, zirconium, and then we had some addition. So they were based on some main element. Then at the end of the 20th century, mostly it was manipulation of microstructure, which became more popular. So grain refinement, different kind of phases, microalloying, that kind of thing. So new alloys were like introduced during at least like last 50 years or so. But then in 2004, there was a new concept which was introduced, which is we now know as high entropy alloys. And I will of course go through that why they are called high entropy. But like I want to mention, it was year 2004 when the first publication came out. And as I've shown you this, so news of this publication was announced in this paper with just like kind of like philosophical and kind of like really pure take, like okay, impure and pure stuff, you know. Okay, so now what is entropy? So I usually like to, yeah, that's the most important thing. What is entropy? So it is a good idea, like if we can like have kind of interactive. So anyone know what is entropy? And remember, no answer is wrong answer. Every answer is okay. Shout a bit louder. What is entropy? Yeah, please.
Bueno, pero es el calor reversible a cierta temperatura dada, ¿no?
Yeah, perfect, perfect. Something else. And we always know that entropy is increasing, right? Yeah, perfect. So it's a function of temperature. So this is what we know, right? In thermodynamics point of view, that this is what entropy is. Very simple, right? And then we also know statistical mechanics definition of entropy. So this is given by this guy called Ludwig Boltzmann. And this is his tombstone, and on his tombstone, like on his grave, this equation is written because he gave us this equation. So that's what he's known for. And also this constant K over here, we call it Boltzmann constant. So entropy really, I mean, he was in statistical mechanics, like it is existence of different possible microstates. That's what entropy in this sense is. But then we have another entropy, which we, as you know that this is about disorder, right? We also, disorder is other way of saying entropy, because disorder is always increasing, especially as a sense of temperature. So the third kind of entropy, there can be many kinds, but here like I just introduced three, like very basic, which you already mentioned, and then statistical mechanics, and then configurational entropy. So in this one, in how many ways we can arrange, if for example we have 5 different kind of balls, in how many ways we can arrange them, right? It's configuration, right? So in some ways they can have less entropy, in other ways they can have more entropy, right? Simple, very simple. And this is given by, so because in alloys we call about mixing, right? We deal with mixing. So we add, for example, carbon to iron and we get cast iron, and we add nickel or cobalt and we get steel, right? So actually we're mixing, that's what we are doing. And the entropy of mixing is, this is how you denote it, how you calculate it. So R is, here is, what is R? Anyone can tell me what is R over here? Huh?
Gas constant?
Gas constant, perfect. Excellent. So this is gas constant, and this is N is number of like things, number of items, and how many you have, like it's I. So it's N log Ni. It's very, very simple, right? And when we talk in sense of alloys, so we can classify them as low entropy alloys, which is most of our alloys, which are based on one element, because you have to, and they have a value less than R. So does anyone know what is the value of R, gas constant? No, you should know, come on. It is 8.3, some,
no? Something like that.
Yeah, something like that. 314 kJ per exactly. Okay, so you already know this from gas theory and so on, right? So then we can classify them into different kind of materials. So low entropy or traditional alloys are those whose mixing of entropy is less than R, which is gas constant. And medium entropy, which is between 1.5 R and 1 R, right? In between that. And if its entropy is more than 1.5 R, then it is high entropy alloys. We are done. Okay. Okay. So now we can classify, or we can draw a timeline for these different kind of systems or alloys based on entropy of mixing, right? And you can see it is log of something, right? Log of 2. It means like 2 element base elements, 5, 7, and so on. So when we were dealing with traditional alloys or conventional alloys, how they are known as bronze, iron, steel, and so on, they were usually over here in the range of low entropy alloys. Superalloys are usually near to medium entropy alloys. And then high entropy alloys, what we are going to talk about in next maybe 30 minutes or so. That will be high entropy alloys. Okay, clear? Okay, perfect. Okay, so I think everyone knows what is a solid solution and what are criteria to make a solid solution, right?
Yes.
Okay, then we can just move to the next slide. Okay, so in solid solution, so we mix something into a solvent. So we have a beaker, which is base, and then we add up something into that, and that's how we create a solution. But what is a solid solution? When it solidify, it should retain its crystal structure, one kind of crystal structure. Then it will be solid solution. But if it does not retain that crystal structure, then it would be intermetallic or something else. Okay, so this is the definition. And the most of the rules which govern the solid solution formation, they are given by this guy called Hume-Rothery. This guy. It is one person, Hume-Rothery. It was William Hume-Rothery. And it is mainly for substitutional solid solutions because interstitial can have different kind of criteria. For example, how we deal with carbon. So here, it will form a solid solution when it has similar atomic radius. If you are mixing, say, nickel into iron, so they have very close atomic radii. Does anyone know what is atomic radius? Like just rough estimation of, say, iron, because you deal with iron a lot. Atomic radius of iron. I think it's 1.26 angstrom, around that. Nickel is also very close, maybe 1.27 or 1.25, something like that. So they are very, very close to each other. So they must have less than 15% difference in atomic radii for them to form a solid solution. Second, they should have same crystal structure, because if you mix with BCC, you know BCC, right? Body center cubic with face center cubic, it would be difficult to make a solid solution. They should have similar electronegatividity. They should have similar valency. So these are criteria which were given by Hume-Rothery. But we will see that in high entropy alloys, these criteria are not followed. And that's why, I mean, you can understand that why metallurgists did not think about mixing so many elements together. Because they were thinking that if we will do that, we will get something very brittle. You'll get intermetallics, which we don't want, because intermetallics are very, very brittle. But solid solution is ductile, but they can also be strong. So that's why no one thought about it, okay, because otherwise they would have broken these criteria. Okay, so now we can define what is high entropy alloy, and we can. So this was the first paper. I will show you which papers those were. Actually, there were two papers. So this guy, Professor Yi, he gave a definition of high entropy alloy, and according to him, now it is more broad, but at that time it was this was the definition which were followed at that time. So it should consist of 5 or more base elements, right? Usually we have 1, but in this case it should have at least 5 or more. And they can be anywhere between 5 and 35 atomic percent. So they don't have to be equiatomic. They don't have to be same amount. They can be very. And you can have minor addition or you cannot. I mean, it's up to you. So this is how it is. Okay, major element 5 or more, composition or concentration between this, minor element must be less than 5%. And this is what I have shown you that that's how you calculate configuration entropy, and this is, gives free energy, right? And when you have high, okay, why you can make solid solution by using this? Because if you have high entropy, then this term will be negative, right? And you want to have negative free energy of mixing, gives energy of mixing for solid solution to happen. So that's how it works. And as I mentioned that mixing of entropy or configuration entropy should be more than 1.5 R, 1.5 R or more. But this was in 2004 when he introduced it for the first time. And when we have multi-component alloys, then what we do, this is conventional system. So you have one main element. This is kind of phase diagram, like just representation of that. And then you add minor elements from some other metals, and you will have this alloy. So we are basically focusing on edges of phase diagrams. But when we have multi-component systems, so we move towards the center of the phase diagram because we are adding like a lot of alloying elements. Right. And when you have different alloying elements, then atomic size will be different. And this is simple solid solution, conventional one. Sorry, this one. So you have, I forgot. Okay, you have main one base, and then you have some additional alloying addition. So you can see how this location moves through it, right? So it will have some kind of resistance because of the secondary elements. But when you add more and different kind of randomly mixing elements, then it will have different kind of resistance because of atomic size mismatches and so on. Okay, we have to move quick. So this was the first paper. There were two papers at the same time, which was published in High-Entropy alloys in 2004. So like 19 years ago, right? So this was the first one. Actually, they were published at the same time. This was published by these people. Basically, Brian Cantor was the lead, and he was at the University of Oxford at that time. And he mixed, I mean, not him, but like his students, undergraduate students actually. That's who really did this work. They did it in 1980s, but then they thought like, okay, this is not useful. So they were mixing like elements from 5 to 20, and they were trying to see what will happen. But undergraduate student graduated, so no one finished that work. So it was just forgotten. But then like after like many years, like he asked some other like undergraduate students to like complete that. So sometimes it's good to complete your work, I think. Okay. So they were mixing between 5 to 20 elements, and they were seeing what happens. So this was the first paper, right? And what happened in this? So this is Brian Cantor, by the way. He was vice chancellor for University of Bradford. He was vice chancellor for York University. Now I think he's retired. He's very, very old now. But this was his work with his undergraduate student in like 40 years ago, in 1980s, right? And you can see that he had been working in metallurgy for almost 50 years. But the only paper like which really, I mean, now this paper like which he wrote in 2004 that has the highest citations. So like you can know, sometimes people can work their whole life, but like still like the most popular paper they are known by, sometimes just happen by accident. Okay, so so this alloy, the one which was proposed in his paper, which I just shown you, it was consisted of 5 elements, 5 consecutive elements from the periodic table. And you can, I think, see them here: chromium, manganese, iron, cobalt, and nickel. So they have very different crystal structure, but still they could form single phase. I will show you like, so now this is non-Cantor alloy because, and they were the first one who is shown. So what happened? So you have 5 elements. In this one, iron, chromium, you know, it's BCC. They are BCC, right? Nickel is FCC. Cobalt is HCP, and manganese is some complex structure. But still, this alloy can form simple phase centricubic single phase. So it does not follow Hume-Rothery rule because according to those rules, you must have similar crystal structure, but it doesn't happen in this case. And they had 20% from each element. So 20% of each element, and ultimately you get this alloy, which now we call Cantor alloy, and it has one single phase-centric cubic structure. Okay. Then at the same time, there was another publication by JWA. He was professor in Taiwan, and he gives the definition of this new system. He also had been working with his students for like 40 years at that time, but they did not really, thought it's really worth publishing. But they also decided in 2004 to publish this one. And that's how like we got initial definition for these kind of alloys. And this is his just introduction, and even for him as well, he had been working for a very long time. Still, like his most cited paper was the same one, which he published on High-Entropy alloys. What I want to tell you by this is sometimes people can just do some stuff which is very unconventional, but very simple. Like for like so many decades, like no one thought about like, okay, you can like add them in this way, and you will get something which can be very, very good. Because if you have phase and cubic structure in this kind of alloy, you can have really good properties, mechanical properties. You can also have magnetic properties maybe. And sometimes their whole career can be like end up like this, like okay, once they publish it and then like that become like really the highlight of their career. Okay, so you give 4 core effects for these kind of alloys. So as we have seen, they have high entropy of mixing. So they can form simple solid solution, because we know from Gibbs equation that if you have high entropy, you can have negative free energy of mixing, and it can stabilize solid solution, right? And so you can get simple solid solutions, right? Second is because you're mixing large amount of different elements, right? They have different kind of atomic sizes. So because of that, you can have solid solution stacking, because the lattice will be distorted, as I've shown you in the previous slide. So the dislocation will face more resistance when they will propagate. So we'll get solid solution stacking from that. Third is sluggish diffusion, right? Because these are like very different kind of structures and different kind of elements, atomic sizes. So you can have lower diffusion rate, and as a result, you can have better high temperature properties. Number 4 is about cocktail effects. Which is understandable that you can have synergistic properties, because you can have different kind of interaction by elements in major amount. And we now, at that time, they had a specific definition that there must be 5 or more elements, and they must be like mostly in equiatomic. But now we have very like kind of liberal or more like flexible definition, and we can call them by different names. So multi-component alloys, because they consist of multi-components. They can be multi-principal element alloys. They can be complex concentrated alloys, compositionally complex alloys, baseless alloys, because they are not based on one single element. So they are different names, but they mean the same thing. Okay. And then they can have very good properties in different ways. They can have tunable properties like hardness, for example. If you just modify aluminum a bit, so it's similar to what we apply in steel, for example, or other conventional alloys. So we tune its properties. We can increase its hardness from like say barely 150 Wicca hardness. It can go all the way up to 700, right? Just by modifying aluminum a bit. And it can have crystal structure transformation from FCC to pure BCC and intermediate. And similarly, they can have higher radiation resistance. So, for example, this paper shown that compared to these alloys, nickel, chromium, cobalt, in equiatomic weight, it had lower, disorder because of irradiation effect. Similarly, there are now a number of high-entropy alloys which are superconductor. So, if you are interested in that field, that can also be you can explore new kind of alloys. Okay. Then also they can have lower swelling against irradiation. You can compare with nickel, cobalt, and 3 element and 5 element, which is Cantor alloy. And Cantor alloy have very, very small kind of swelling when we compare it to, say, pure nickel. Again, it is because of this multi-component effect. It's too small, but I think, I don't know if you can see properly. But what it says over here that high entropy alloys can have different kind of properties, and because of that, it can be adopted for different kind of applications. So it can be structural or functional, right? You can have high temperature properties, and you can use it for turbines. It can have cryogenic properties, which you can use it for, say, liquefied natural gas handling. Then low density energy absorption for different kind of applications. High hardness, for example, for ballistic applications, for cutting tools, and so on. You can have different kind of properties, shear memory effect, high capacitance, and you can like think about different kind of properties and then applications. So it is a very hot topic, so you can like find something new. You can like just try it and you will get something like that. So it's really good to get into this. Okay. So because I'm a metallurgist and I mostly deal with structural applications, basically mechanical behavior. So I will just show you like what happened with regard to structural high entropy alloys. Until 2014. So the first publication came in 2004. But until 2014, for 10 years, for first 10 years, it was almost unknown field. No one paid any attention to this. People were thinking, okay, this is just like die out very soon. But in 2014, it really took off, and I will show you like which publication really broke the camel's back. And they can have a high fracture resistance, right? They shown in 2014. Then phase changes, then dual phases. So you can have kind of a trade-off. You can get rid of trade-off for strength and ductility by using this mechanism. Then multi-phase high entropy alloys, then phase transformation. Similarly with high pressure, you can have phase transformation. Then single phase high entropy alloy by carbothermal shock, and then kind of superalloys. We now call them high entropy superalloys because you have gamma phase similar to conventional superalloys, which is FCC, and then you have precipitates. Kind of here we have L12 kind of precipitate. Usually coherent precipitates, and they can have really good properties for high temperature applications. And then you can, now they are being 3D printed. You can have a phase interface design. You can like, and also you can have metallic glass via electrosynthesis. So it's just timeline for structural high entropy alloys. Okay, now I will talk about deformation in high entropy alloys because that's what I do. And I will very quickly go through first room temperature, then high temperature, and then I will come to low temperature. That's my area of focus. Okay, so because it has 5 elements, so this we are talking about Kant alloy, which have 20% for each of chromium, manganese, iron, cobalt, and nickel, phase and cubic structure. So they were expecting it to have very different kind of mechanical behavior. But when they did deformation studies, this is the neutron diffraction, by the way. That's what I work with as well. So they saw it have anisotropic behavior, similar to simple phase and cubic alloys, like how you would expect in, say, austenitic stainless steels. It was similar to that. This is from its lattice stream, which was similar to what we observed for because of dislocation slip. Similarly, its texture was similar to FCC systems. It was mainly dislocation slip, which was facilitating deformation. And its deformation was facilitated, but this was a big difference. It was mixed of both edge and screw dislocations. I think you guys know that mostly it's edge dislocations which are active in phase and cubic systems, and mostly screw dislocation which act in BCC. But here they found that it's mostly mix of both of them. Okay, so basically dislocation slip, which mainly facilitate deformation at room temperature. Now for high temperature, so these are stressing curves at 800 Kelvin and 1000 Kelvin, right? Now you can see for 1000 Kelvin, like it does not have much strength. For 800 Kelvin was good, okay, but here like it's like barely anything. When they, okay, similarly again it's neutron diffraction, like that's how like I usually like explain my literature review. So in this case, so the latest strain developed, which is intergranular still, because we have multi-poly crystals, and different grains have stresses or strains in between them. And so stresses develop in a similar way as I've explained for phase static cubic systems. Similarly, this is texture evolution, texture change, which also happens similar to FCC systems. So this is at room temperature. Similar peak broadens. But when we go to 800K, still it's a bit similar. Of course, intensity does not develop that much. So texture does not change that much. Because, for texture change, you have to rotate grains, right? But here, it's like a grain rotation is happening, but less. But when we go to 1000 Kelvin, you can see no intergranular stains, no texture change. So the deformation, we can see that room temperature 800K, it is basically dislocation glide. But at 1000 Kelvin, it's just dislocation creep. That's what's happening at high temperature. And then at high temperature, we can also have, for these alloys, we can have superplastic behavior. Superplastic means we can have very high ductility at high temperature. So you can see it is like the ductility or elongation is more than 300% at 1023 Kelvin. And the deformation is basically by grain boundary sliding. So this is comparison with some superalloys. And the point is do they have better high temperature properties? So it depends on which alloy you're talking about. There are different multi-component alloys. So up to 1000, they seem to perform better than conventional superalloys. But after that, it depends. So it's kind of like an open question, and it will take maybe decades before they will be really put into applications. But there is a lot of research going on at high temperature, high entropy alloys. Okay, then what will happen at cryogenic temperature when you go below room temperature? Can anyone tell me what we expect, what will happen at low temperature? I want to drink water so that I can listen to answer. Okay. Yes, please.
We can expect lower.
Yeah, you have to. Lower properties. Which lower properties? Mechanical, electrical, magnetic. Because mechanical. Which mechanical properties? We have hardness, strength, ductility. Ductility. Perfect. So usually at cryogenic temperature, you should expect lower ductility. And in some cases, you will have ductile to brittle transition, which means the material will become completely brittle. So that's how I started my research with the high entropy alloys. So this was, as I was mentioning, that for the first 10 years of high entropy alloys, people did not pay much attention to high entropy alloys. They were not popular at all. I mean, maybe few people are working, but that's all. Then this paper came out in 2014. We said that they can have high fracture resistance at cryogenic temperature. So they can be really good for cryogenic applications. And this study was actually led by one of very prominent metallurgists called, sorry, I have to go back, Robert Ritchie, we just call him Rob Ritchie. So even for him, okay, did I miss one slide now? Okay. So even for him, you can see he had been working in metallurgy at Lawrence Berkeley National Lab and at California, called, what is that? I forgot his other affiliation, but anyway. So Berkeley, he was working at Berkeley University. So even for him, you can see, he graduated, I think, in 1960s. And he had been one of the most prominent metallurgists. And still, you can see his most cited paper is the one which he, when he was working on high entropy alloy, the first one. And since then, really high entropy alloy took off. Okay, so now why cryogenic applications are important? So this is one of example which I think very important to show. So this is a space shuttle. It was called Challenger. And it flew from Florida in 1986, and it had 7 astronauts on board. But as soon as it took off, within seconds, it collapsed. like there was explosion and all people on board died. And it was a very debated issue. And there was a commission set up called Rogers Commission for that, to understand what really happened, whose fault, who to blame. You know, that's what happened. Like when something goes wrong, when something works, like then everyone wants to take credit. You know, when something goes wrong, then find who to blame. So this inquiry, Rogers Commission, had a very prominent person. I don't know if you guys know Richard Feynman. He's considered one of the best physicists after Einstein. He was an amazing guy. So he was in that commission, and he also worked on this project on nuclear weapons. So he had a lot of experience working on different kind of applications related to space and to weapons. And you can see Neil Armstrong next to him, the first man on the moon, right? Okay, so Richard Feynman on that day, like when he came to inquiry, he brought a vernier caliper with him, sorry, micrometer screw gauge with him, and he brought one of the sealing O-ring. You understand, like this O-ring. And he also brought an iced water cup. So he dipped this O-ring inside that iced water, and then he just applied pressure with micrometer screw gauge, and it fractured. So that's how, like, he very brilliantly and like in a very simple way, he explained like what really happened. Because temperature was very low on that day in Florida, where like this took off. And because of that, there was contraction, right? Because of this, because you have to have like in for aerospace spatial, you have to have it sealed completely. But because of contraction, so it was not properly sealed. And that's what ultimately led to the failure. So the brittleness is mainly the issue which really happened. And like it contracted and then it just fractured. Okay. And there are a number of applications which where we use where we need materials for cryogenic environments. So most important one is exploration of outer space. I mean, there are missions which goes to different planets, and even when you fly, if you fly on aeroplane, you will see when it is like really high altitude, you will see it will show the temperature of outside, and it will be like minus 60 degrees centigrade, minus 70 degrees centigrade. So it will be very low temperature. So you have to devise material for that, but that is like still not that low as this one, which is like almost close to absolute zero. What is absolute zero, by the way? Yeah, perfecto. And which is the material which is the environment, which is material which is the lowest, have the lowest temperature? You know what is the temperature for liquid hydrogen? Sorry, liquid nitrogen. 74. Close, 77 Kelvin. So 77 Kelvin, that's liquid nitrogen. Then there is liquid hydrogen, 15 Kelvin. Liquid helium, 4.2 Kelvin. So that's like how like the lowest we can usually go. I mean, of course, for fundamental physics, they can go to millikelvin, but for usual application, liquid helium, that's what we get, like 4.2 Kelvin. Okay, so I was talking about different applications. Similarly, superconducting magnets, which they are used for fusion reactors, tokamak they are called. They become superconductors at close to 4 Kelvin. So we need materials for that as well to hold this gas. And then underground power transmission cables, because they are carrying like huge power. So we have to like cool them down. Similarly, we also use them for NMR, which is neutron magnetic. What is this? What is NMR, by the way? It's nuclear magnetic resonance. And the MRI, magnetic resonance imaging. So these are some applications which I was saying. Okay. So this was a publication in 2014, where it is shown that at room temperature, you have strength, this much ductility. But when you go to low temperature, 200 Kelvin or 77 Kelvin, say, strength increases. That is understandable. Why? Can anyone tell me why strength increases at low temperature? It has got something to do with the dislocations. What happens to dislocation at low temperatures? I mean, the movement becomes slow, so you will have like higher, it will take more force to move dislocations. So the yield, what is yield strength for a material? When will a material yield? When you will move dislocations, that's the time when material will yield, right? And when at low temperature, you will have more resistance against movement of dislocation, so that's why it will have higher strength. And but in this case, they also seen that, which is common, like this is like understandable, but ductility there was very different, so they could not explain like why like it had like very high ductility at such low temperature. And Ritchie, the guy we were talking about, he specializes in fracture toughness. That's his specialty throughout his 70 years career. Okay, 70 is maybe too much, maybe 60 years career. And so they found out that mostly fracture toughness decreases at low temperature. But in this case, they saw that fracture toughness was almost more or less similar as at room temperature. And they associated it with twinning. So you have seen at room temperature, we had slip, dislocation slip, right? Here we had, they saw nanotwins. I don't know if you can see it. They are usually parallel. And because of that, so this plot is very, very popular. We call it Ashby Map. You will see it in your textbooks, and everyone loves to use them in like high profile papers. So they put like here, like you can see fracture toughness and yield strength over here. And these are all kind of materials, and high entropy alloys are here because they have very high yield strength. But not that, but not only that, but also they have very high fracture toughness. And because they mentioned about twinning, so I think I should introduce here different kind of stacking faults in phase cubic structure. So FCC, you know, it's arrangement. It's a closed back structure. So it's layer of A, B, C, right? 3 different kind of atoms. I think I don't have to go into detail actually. You might have learned in your class already. So if you remove one layer, if one layer is missing, then that stacking will be similar to HCP, because HCP is kind of like AB, so on. And similarly, if you have an extra layer, so when you remove a plane of atoms, it's called intrinsic fault, right? Is it? Am I correct? No? Okay. You can see over here, sir. ABC, then A is missing over here. A plane is missing. And when you have an extra layer, an extra plane of atoms, an extra layer of atoms, then that would be known as extrinsic fault. It means you have an additional thing from outside. Okay. And how do they form? So basically we have dislocations which are perfect. When they split, and why would they split? Because of yeah, exactly. So it means like they are not stable. So if they have high energy, I mean their energy is not stable, then they have to split so that their energy can come down. So if that happens, then we'll have two partials. Partial mean like half parts of dislocation, and in between we'll have a stacking fault. And for stacking fault to happen, you should have lower stacking fault energy. I think you might have already learned that in your class. And this is the reaction which happened. This is like very fundamental. And stacking fault energy can relate to stacking fault probability. So you have lower stacking fault energy, you will have higher stacking faults, right? Clear? Okay. And then this stacking fault energy also depends a lot on temperature, and that can also tell us different kind of mechanism which can happen. So at high temperature, you usually have displaced cells. Then at low temperature, low stacking fault energy, at low temperature you can have twins, or you can also have Martin-City transformation. Okay, I think I have to go quick now. Okay, low stacking fault energy, you should have phase transformation, and you will have early onset of twinning or stacking faults, and you will have multiple deformation mechanisms. And that's where like I started this work. I mean, for that we have to do some in situ study and use neutrons for that. That's why it will be a, suspense. Okay, so this is how a sample, you already know like tensile sample, so we stretch it. And this is we are cooling it with liquid helium. So we can achieve low temperature. So in this case, we could achieve 25 Kelvin, depending on which kind of material we use. And you can see it have different, so this, you have seen XRD, X-ray diffraction pattern, which have diffraction peaks. This is similar. So you can see different peaks like 111, 200, and so on, right? And this is lattice spacing, respacing. And then from this, you can see different kind of faults. So at room temperature, you can see there is no, they are very symmetrical peaks. When you go to low temperature, they become asymmetrical, which is because of different faults, stacking faults, deformation twins. Okay, I already mentioned, okay, when peak shift, then that's stacking fault. When peak broadens, that is because of dislocation. But asymmetry, that is because of twin faults. So you can see here the peak have shifted a lot, right? But here you don't see much. Here you can see peak broaden more than here, so dislocation will be higher. And here, like you can see a lot of asymmetry, so you will expect twins over there, deformation twins. And you can see like at 3 temperature, this is a different alloy, and you can see at 15 Kelvin, of course, strength increases, ductility also increases. So we see even at 15 Kelvin, so it's a lot of ductility, but something else happen as well, which I will not explain. Okay, and it have high strain hardening rates. You can see like at room temperature, it is going down, but here it is like almost stable. And also its fracture is characteristic is a bit different. So this is microscopy image at low ionization, I would say. That you can see at room temperature, it had necking. That's how ductile fracture happened. Because the material, if you can see here, it had 45% ductility. But at low temperature, 15 Kelvin, it had 62% ductility, but still it fractured like without any necking. So that is also, it means it have more uniform elongation because of these planar faults, stacking faults, twin faults. Okay, and then we can also, this is comparison for stacking fault probability. At room temperature, almost no stacking faults. At low temperature, you can see significant increase in stacking fault probability. This is texture. At room temperature, this is room temperature. It is like continuous texture change. Grains are continuously rotating because of this rotation slip. But at low temperature, initially it is going straight, but then it somehow does not change much. So because of different mechanisms. And from TEM, I think all of you are aware of transmission electron microscopy. So you can see at room temperature, these are dislocations. Some twins, but at 15 Kelvin, you can see stacking faults over here. You can see a lot of twins, even intersecting twins. And here is high resolution TM, which shows twin faults. And these are twin fault boundaries, which I have marked over here. And you can see also, so this is a martensitic transformation, one of the alloy. And at room temperature, it did not have any addition peak. But at low temperature, 140 Kelvin, it had some bump, which was related to HCP phase. So the phase in a cubic was somehow transforming to HCP, but transformation rate is very, very low. Okay, this is 3 different kind of alloys, 3 element, 4, 5. So how stacking fault energy differs for them, and as a result, stacking faults start early. So this is, I put deformation strain, and this is temperature at 3 temperatures. So at room temperature, it takes more deformation for stacking faults to become active, to reach that level. But when you decrease temperature, it starts early. But for alloys, because the stacking fault energy is different, so this one has the lowest stacking fault energy, so it will have early activation compared to the one at the top. By the way, they are all FCC. Okay, so because I'm a metallurgist and mainly high-entropy alloys started as alloys, but now they are really divided into different kind of fields. So now they are known as high-entropy materials. So you can have, initially it was just high-entropy alloys, then there were high-entropy ceramics, and then even 2D high-entropy materials. So now they are more like everyone somehow using high-entropy concept to gain new kind of insights. Okay, and mainly they are like this tetrahedron, I think you all know in metallurgy. This is like in fundamental, like how structural properties, applications, how they are interconnected. So in high entropy alloys, so you can have different synthesis route, which you can see here. They can be equiatomic or different kind of like non-equiatomic. Then you can have different kind of properties. Then you can expect different kind of microstructure. And you can also apply modeling to estimate what you would expect. And I would just finish with this one, that because they are multi-component alloys, there are a lot of issues which need to be resolved for them. So if you want to work with them, I think it will be really good because you can explore really new things that could be really nice. So question is about their phase prediction and stability. Because some of them can form simple phases, but some cannot. Even like with like more element, they should be able to form single phase solid solution, but they cannot. So what is the reason for that? So people have some ideas for that, but I think they can be more explored. Then similarly, strengthening theory for them is non-consolidated because they are complex, and really it is really hard to pinpoint how much different mechanisms are contributing. So that is one of the point. Similarly, their ductility increases at low temperature, as you have seen. And people say that is because of stacking faults or twins or transformation. But the thing is, steel, for example, arsenic stainless steel, question which need to be answered. And similarly, there are some issues about them regarding their stacking fault energy, because it is really not easy to get their stacking fault energy, and it does not follow any criteria. And also they have short range order, which is also unresolved. So I just because I was running out of time, so that's why I just quickly went through them. But you are more than welcome to have discussion like later on if you want, or if you have any questions. So the point which I want to make is that there are a lot of opportunities in research for high entropy alloys. So if you want to pursue your research, if you are thinking about your project, I think this would be really good. Thank you very much. Sure. Okay, any questions?
Okay, thank you so much, Dr. Naeem, for the excellent presentation. If you have any questions, please let me know. You can ask in English or in Spanish, and if it's in Spanish, I will translate for you.
Okay. Please.
When you were saying the location can drop or can multiplicate, and when the dislocation are being more keep growing the number of the dislocations, it makes that growing the heart.
Just start moving, and once they start moving, they will multiply. They have a dislocation source, so-called Frank-Ritchie source, and then we have more dislocations. So when I say like a low temperature, for example, it becomes difficult because it had to overcome that before it have yielding. So at low temperature, that stress level increases, and that's why we have like hard yielding. Little bit clear? Okay, perfect.
Will you talk about the multi-component metal material?
Yeah.
You mentioned the sludges diffusion.
Sorry?
Can you tell me which kinds of defects have these effects?
Which kind of defects for what?
In sludges diffusion.
I didn't get that. Maybe you can say in Spanish and Dr. Liana can translate that. Because
Cuando mencionaba exactamente multi multi-component metallic material, menciona la parte de distortion.
Okay.
¿Qué efectos están produciendo ese incremento en la temperatura o cuáles consecuencias del otro?
Okay. When you talk about the Lewis diffusion and multi-component alloy, the question is what effects are related to this
Oh, it can be any defects. As you have seen, dislocation is one defect, right? Stacking fault is another defect. Then you have twin fault, that's another defect. Then within phase and cubic structure, if you have HCP, that's another defect, right? And you can also have vacancies, right? Within, like when you have, especially at high temperature. So the point is at which temperature. So they can vary, like at low temperature, maybe you can have more planar faults. At high temperature, it's mostly dislocations. Yeah. Yes?
I have a question. Does all the high entropy alloys have stacking fault probability?
No, stacking probability means if it can form stacking faults. So it depends on kind of alloy, composition, right? Temperature. These are the two main factors. So some of them may form stacking faults, some of them may not. So I've shown you some example, for example, Kent alloy at room temperature, no stacking fault. But at low temperature, it does form stacking faults. So probability is kind of like what are the chances of making, producing stacking faults. Any other question?
Okay, you mentioned that in the presentation, but was not very clear for me. Why is stacking fault energy from second phase?
Okay, because the alloy which we have is metastable. If it is stable, it will just deform by dislocations. But when it is metastable, which means is, for example, Kent alloy, or the other one, chromic cobalt nickel. So it is metastable. So that's why it can form stacking faults. And I mentioned that stacking fault. So if you have one intrinsic stacking fault, if you take out one layer of one layer of FCC, then it's AB stacking. Then it's two layer of, which is HCP. So it is one layer of HCP within FCC, but we don't call it HCP, we call it intrinsic stacking fault. But when you combine multiple layers of this intrinsic stacking fault, then you generate HCP phase. And the point is because they're metastable, so the more are kind of unstable, so the more instability we have, the higher chances it will be for them to convert from this crystal arrangement to another one. So with decreasing temperature, that's what happens. Because in order to reduce their energy, they have to split. And then ultimately they combine like layers of intrinsic stacking fault, and ultimately it will become HCP phase. Clear? Good.
What happens with the education at the room temperature? What happened with the dislocation at room temperature in the HEA?
What happened? Amazing.
What is the role?
Okay. Because how we deform materials, that's what happened. So if I want to, for example, if I put tensile specimens in the machine, it will stretch. So what is happening? It have dislocation. It will accommodate more dislocation. Ultimately, those dislocation will move, and by movement of dislocation, that's how material deform. So that's the main, like you can say, thing how like whenever I do rolling or anything like that, that all is thanks to dislocations. On one hand, dislocations make materials imperfect, right? Because this is a fault, this is imperfection. So, but at the same time, they are very useful, especially for structural application. That's how we can make them very strong, especially if we do thermomechanical processing, if we do rolling or something like that, they become very strong.
Please.
is the problem? The problem to create high-entropy alloy.
What is the problem? They don't have any problem. They're perfect. No. Main problem for making high entropy alloys? It depends. If you're talking about their disadvantages, of course they have disadvantages. Like they can be, because you're adding a lot of alloying elements, so they can be very expensive. That's one problem, for example. Another is not all of them can form like simple solid solutions, which is not a bad thing, by the way. Sometimes you really need, like, for example, superalloys. They
have to fabricate high entropy alloys. You say that the tools, they're not, no funcionan, right?
Yeah, the question is what rules do you follow to fabricate high-entropy alloys? Because components.
Oh, yeah, they have some rules. There are some parameters. For example, one is valency parameters. One is about their atomic radius difference parameters. But the thing is, they are not really unified. In a way, like people are still trying to, like, still it is at that stage where people are just trying to mix up and to see if it works or not. I mean, not exactly like that, but I'm like exaggerating. So you can do first simulation or modeling to see which kind of phases to expect. But as I was saying that now we don't focus on just single phase high entropy alloys. Now we just name single high entropy alloys, but now they can be like multi phases as well. The thing is, they have some rules, but sometimes they also work and sometimes they don't. The thing is, because it's a very new field, and like composition space is very, very wide, so we can have like trillion of alloys, like we mix all of these elements in different kind of combinations. So there are some rules, but still they are not that well defined. Sometimes they work, sometimes they don't. And but simulations can really help with that. So that's why a lot of people are doing calculations, DFT calculations, or initial simulations, something like that, to understand like what could be the optimal way to obtain these alloys. Here in the front.
Do you think?
Don't be so loud.
Do you think there will be a moment where the lead
Say that. She's working steel. Professor Gonzalo is here. I cannot say that. No, the thing is, high entropy alloys, they're a new field. And we don't know where they will end up. There used to be a new field like 20 years ago, 30 years ago, called bulk glasses. I used to work in them. Now it's almost gone. No one work in that. Like people are thinking like there is a lot of potential and like it will like really take over everything, but nothing happens. Okay, but I can say this, that it already have applications, especially in coating, because you can have really, really hard coating. You can have a lot of functional applications as well. But replacing, say, steel will be very difficult because these are very expensive, and in business, in industry, everything is about money. Exactly. So I don't know, like maybe like it will replace like some of it, but I don't like when and how much. That will be difficult to say. But totally, we can dream on. Maybe one day.
¿Alguna otra pregunta? ¿Gabo?
how is possible that the high entropy alloys have a high utility if they have a lot of elements? I mean, if the number of the location doesn't decrease, if they have a lot of elements.
So you're saying that distribution number does not decrease because of a lot of elements? No, I did not understand.
¿Cómo es posible que los esos datos los voy a tener en la alta velocidad si el número de rotación no lo ofrece a la vez.
Okay. How the high-entropy alloys can have high ductility? I think a low temperature, right? The question is a low temperature? Or any temperature? Okay. How the high-entropy alloys can have high ductility? The question is what happened with the dislocations? They increase, what happened?
I see. So a material to continue deforming without fracture is to do with uniform deformation. You know this, once you have a crack developed in that, if the deformation becomes non-uniform, then you can have kind of like a weak link and it will fracture over there. But the special thing about them is at low temperature, they don't have necking. So you don't have kind of non-uniform deformation. So it remains uniform. With regard to your question on dislocations, so usually you would have higher dislocation. As you keep deforming, you will accumulate dislocations. And dislocation density for them is very high at low temperature. So mainly it have to do with uniform deformation. That's why they have a higher ductility. And for that, you have to have different kind of deformation mechanism coming into action to facilitate that.
¿Has aplicado técnicas de optimización computacionales para obtener empresas de amplitud?
Have you applied simulation or any other computational technique to design high-entropy alloys?
No, I did not. But usually, you know how it works. So when we do research, so we collaborate with different people, or people who are working in our own group. So some of them can be a simulation person because that's very specific field. That's how mostly it works. That some people are doing simulation, some are doing experiment, and then at the end they combine. So I personally don't do any simulations. I'm an experimentalist, so I must perform experiments. But there are people like in our group are like we collaborate with who do simulations. That's how science works.
Hello, thank you very much for the presentation. My main question is, all the high-entropy alloys need to be out of equilibrium, they are metastable, or there's a point working phases when you have a continuous application
Stress.
working condition for each kind of alloy, there's a point you can find the equilibrium states.
Did you get that question?
No, sorry. I understand like metastable, but
Todas las aleaciones de alta entropía tienen que ser metastales para el equilibrio. Y si en algún momento, en cuestiones ya de aplicación, se encuentran estas condiciones donde pasan a ser de equilibrio.
The question is if all the high-entropy alloys are materials out of equilibrium, means metastable, or if some high-entropy alloys, when they are applied continuously, like some industrial application, they can find somehow.
no. The thing is like we usually take metastability as a good thing because you can manipulate it for specific applications. Because you can have maybe higher strength when you have a phase transformation. Similarly, you can have higher ductility because of that. But for example, this alloy, this does not transform. This remains like, if you see these peaks, so this is like starting point, right? And these are phase center cubic peaks, like 1, 1, 1, these are written over here. During deformation, you don't see any new peak. It's still FCC. So it depends on application. Some application you cannot afford metastability. You cannot afford transformation. For example, for magnetic applications, because some structure, if it's in FCC, it can be like non-magnetic, but if it become a different structure, it can be magnetic. So to avoid that, you don't use for those kind of applications, but some other you can like optimize for your requirements. You're welcome. Eyes were equimolar. That was true. Like that's like what I introduced. That was mostly like equimolar. But by rule, it's not a binding. I mean, you can like vary. The thing which you're asking, like, what was the third one? I actually also forgot what was the third one. But we can look at it. Which will be a combination of maybe 2 or 3 of those. It should be here. Oh yeah, it is minor additions. It's the same. So you can have just equiatomic, you can non-equiatomic, and third one you can have additions as well. So which is similar to what was said in the first paper. That it can be like, but now the difference is like now we don't focus on at least 5 elements, it can be even 4 elements. That's okay. Still it can be high-entropy alloys.
Thanks.
You're welcome. Okay.
¿Alguien más tiene preguntas?
I think we should have to like do that. Okay.
My question is about if there's any relationship between the temperature and the stocking full area.
I shown that. You should remember that. Okay, I can go
Can you
back.
repeat that?
Okay, here is the relationship. Do you see it? So stacking file energy, temperature, and these are different mechanisms. So at low temperature, you usually have low stacking file energy. This is usually I'm talking about by the steel. This is the example of steel, not high entropy alloys, but more or less for alloys, that's how it works. Doesn't matter if it is high entropy alloy. And I also shown you in different from some other results which I actually know. Here I did not say stacking fault energy, but I said stacking fault probability. This is stacking fault probability. So at room temperature, which is 295 Kelvin, no stacking faults, 0. At 15 Kelvin, you can see stacking fault started somewhere here. This is yielding and stacking fault going up. So in general, when you decrease temperature, stacking fault energy decreases, usually, but there can be exceptions. Okay. Cloud? Okay, any more questions?
¿Alguien tiene más preguntas? ¿No? ¿Seguro? ¿Expertos? ¿Analizan esta partida?
Yeah, now they should be expert.
Then only one last question from my side.
See?
Self-publicity. Can you please talk about the opportunity that the students have to collaborate with you? Like do some projects?
Wow, this is the best part. Okay. Okay, I like this kind of question. So, as you have seen, I worked with high-entropy alloys. If you don't, if you have any doubt, then you can talk to me later. I usually do neutron diffraction, which I'm giving a short course in from 3 to 5, yes, today as well as for the next 2 days. So if you are interested in working on high-entropy alloys and also interested in somehow in neutron diffraction, you can come to talk to me while I'm here for next 2 days. You can also talk to Dr. Liliana, and I will be more than happy to discuss. If you have any questions, if you want to know what you want to work on, I'll be more than happy to collaborate.
Thank you. No more questions? Sure? Okay. So thank you so much for your excellent presentation, Dr. Naeem. We were very glad, and I'm sure that we will learn a lot. Thank you so much.
Thank you very much. Have a good evening.
See you